Hello, in this video I'm going to look at using polymorphism and object-oriented programming to make our application development simpler, and I'm going to demonstrate that through the use of a simple computer-aided design-like application. But you may have noticed I'm not in my usual programming place. Well, it shouldn't be of any surprise to you that I'm actually full-time employed, and sometimes my job requires me to go out on the road and stay in delightful hotels such as this one. Nobody ever said programming was glamorous. And travelling around with work like this has completely ruined my YouTube schedule for the year, so those of you expecting to see an update to the top-down city-based car crime game, well, I might tag something on at the end of this video if I've got a couple of minutes to spare. However, that's been delayed a week. So this video I thought would be useful to do something to enhance sort of the C++ basics, and we'll look at polymorphism, a very useful technique.
Now I thought to be different. Instead of using games to demonstrate polymorphism, I'm going to create a small application, a very simple CAD package. So here I've got a matrix of dots which the cursor can clamp to, and we can see we've got some axes. And the middle of these axes represents 0, 0 in our world. Now if I press a particular key, I can start to draw a shape, and we'll see two little red dots that allow me to manipulate the shape. So there we've got a box, and here I can draw some lines. Just sort of throw them around all over the place at the moment. And we can draw circles too. You can see the radius is a line surrounding by a circle shape. And there's some other nice features too. I can zoom in and pan around. Now of course we've done panning and zooming before, so I won't go into too much detail about how I do that in this video. And I can also place my cursor over any of the red dots and tweak the shape's positions. Oh yeah, before I forget, there's one more shape too, and this is a multiple construction shape that gives us a spline. So we can define curvature. Very nice. And you might be thinking, well, what's this got to do with polymorphism? Well, it's difficult to graphically show polymorphism, but here all of the shapes are effectively the same object to the code underneath. Of course the shapes are unique in that they are circles and squares and lines and splines, but the code that will handle these shapes doesn't really know about that, and it doesn't care either, which means making our application can be quite a simple process, because instead of trying to handle all of these different shapes uniquely, we'll let polymorphism do it for us.
Now, some of you not familiar yet with polymorphism may already be thinking of ways to handle this. We could have lots of objects for all the different types of shape, and our application sort of interrogates those objects one by one depending on how it should be manipulated or drawn to the screen. Perhaps another solution is to create one type of object which is all of the objects, and the object itself can self-determine what to do in a given scenario. Approaches like this are valid, but they can be a bit messy, and we may as well use the tools that C++ provides for us to do this. And the primary tool, and what this video is about, is polymorphism. We'll engineer our code in such a way that the compiler can decide at runtime which methods to call, what shapes to draw, and how things should look.
Now I will start by saying that polymorphism is not a beginner topic. Although the way I'm going to show it in this video, we're really only going to start looking at it at the most top level. Object-oriented programming and polymorphism is a really rich and detailed topic in its own right, but you can achieve quite powerful things just by knowing the very basics. For this video, I'm going to assume you do know a little bit about classes already. And although polymorphism does exist in lots of different languages, I'm going to be specifically looking at C++. Let's start with a simple class, in this case called A. And A has a function called doSomething. What the doSomething function does depends entirely on what class A is. Now I'm going to assume that we have a set of structures in our program that are all quite similar in nature, i.e. they have a lot of commonality between them. So I'm going to try and package that commonality up in class A to turn it into a base class. This of course means I can derive from my base class more classes. In this instance, class B. Class B inherits all of the methods and attributes from class A, assuming that it can due to whatever access specifiers we've determined are on those properties of class A. But let's for now assume that everything is public and easily accessible. If I create an object of type B and call the doSomething function, then that doSomething function is defined by the base class A. I can, of course, override the doSomething function by simply redefining it in class B. Now, if I create an object of type B and call the doSomething function, it will call this one instead. And it goes without saying that if I create an object of type A and call the doSomething function, it will call this one. Perhaps I have another derived class, class C. Well, exactly the same thing applies. This too could have its own doSomething function. So far, so good, nothing out of the ordinary. But we started this with a particular caveat, and we said that these classes that derived from class A were in some way similar, and we created class A as a base class to encapsulate the common functionality between the two derived classes. And in applications, it's useful to group things that are similar together. And so how can we do this? If I create an object of type class A, it is very clearly defined as being of type A. Likewise, if I create an object of type B, it is very clearly defined as being an object of type B. It is not an object of type A. Even though B inherits from A, it is defined as being B. Naturally, the same also applies to an object of type C. When we want to group things that are similar in C++, we have several ways of doing this. One approach is, of course, to use an array. But whenever we specify an array, all of the elements of the array are of the same type. Perhaps we could use a vector. But again, the same problem applies. We have to nominate a type for our vector. In fact, any of the standard containers will have the same restriction. The convenient thing to do is to hint to the compiler that B and C are in fact derived from A, and that our vector and array only stores elements of type A. Well, this is quite nice, and we're almost there, but if I wanted to use a specific element of our vector of type A and call our doSomething function, as we saw before, it's going to call the doSomething function defined by class A. We've still not got the flexibility implied to look at the derived classes, and that's because all of our objects are of type A. Instead, I'm going to do something that appears a little strange. I'm going to create an object of type class A. But I'm not just going to create an object, I'm going to create a pointer to the object. And so this means now when I'm creating a new object, I need to use the new keyword or a smart pointer equivalent. But now I can do something a bit special. Because B and C were derived from A, and all I'm storing is a pointer to where A might reside in memory, I can actually create a new object B. And of course, I can do exactly the same for my class C type. So now, when I create my vector to hold my similar objects together, I'll make it hold some pointers to class A. And through some smoke and mirrors implemented by the C++ compiler, what we are implying here is that if classes B or C override a method in class A, then if we were to call such a method, in this case our doSomething method, that it will call the appropriate method related to the class that was constructed. And that's quite a complex and powerful thing. I can now store in a single container a group of similar objects that all have unique functionality, but a common interface. In effect, we have allowed the base class A to morph into multiple subclasses, i.e. polymorphism. We have eliminated the need to manually check what the type of each object is and perform the required functionality we're requesting at that point in time. But it's not quite as simple as I've just made it out to be. We need to hint to the compiler which functions we're likely to be overriding. Here is a very simple class definition for type A. We can see I've got the void doSomething method. That's the one we've been trying to override with our subclasses. If, as before, we just directly called the doSomething method on the object stored in our vector, regardless of whether that object was of type B or C, it would still call the doSomething method related to class A. We need to tell the compiler that doSomething is a candidate to be overridden by a base class, and we can do that with the virtual keyword. This hints to the compiler that I may be overridden. If I'm not overridden, then any call to the doSomething function will naturally be implemented by the base class, i.e. whatever code is written here. So if it is overwritten, it'll execute the overwritten code, but if no override is provided, it'll execute this default code. And there's one last philosophical thing to think about here. It may be the case that class A on its own doesn't make sense. The sense only comes into it once something has been derived from class A, i.e. we've created classes B and C. In which case, class A is really just an interface to its subclasses. On its own, it can't do anything useful, and we'll see an example of that in this video. Well, instead of providing some default code that doesn't do anything, and to force the programmer to provide an implementation when anything derives from this class, we can tell the compiler that this class is an abstract encapsulation by defining our virtual method here as being pure. And you can't create an instance of an abstract class. So if anybody now tries to create an instance of type A, it will fail and throw an error to the programmer, because no implementation of this function exists, even though something potentially can call it. And so this is a very powerful and useful way of wrapping up your program's structure. Now, I appreciate to some of you this may all seem incredibly alien, but don't worry, I think the example code that's coming up really shows the power of this in a nice way. So let's briefly take a look at the class structure for the CAD program I demonstrated at the start. I have a base structure called S-shape, and from that basic structure I derive unique classes that represent the shapes that I have. So a line, a box, a circle and a curve. All of these things are indeed shapes, so it's very useful to recognize them as a singular shape, but they look differently. So I want each of these classes, line, box, circle and curve, to be responsible for drawing itself. So they will all have a method, draw, which draws it to the screen. So it seems that draw is a great method to be thrown into the base class. The shapes are fundamentally defined by nodes, points in 2D space. And the curve is the oddball one here, as it's defined by 3 points in space. So all of my shapes are also going to have a common vector of type S-node, a simple structure. And our node will contain the X and Y position of its location in space, and a pointer to its parent. And this is so when we select a node later on, we can immediately get access to what shape is it connected to.
A valid thing to shout out here would be, but Javid, we're talking about object-oriented programming, why are we not using classes? Well, classes and structs to the C++ compiler are absolutely identical except for one thing, and that is the default access method. For a struct, all properties and methods, well, they're public, and for a class, they're all private. And so it really doesn't matter, unless you're an object-oriented programming enthusiast.
Naturally, I'm going to start by using a skeleton OLC Pixel Game Engine program. And if you've not heard of the Pixel Game Engine, it's a very simple technology that I've created that allows you to draw things to the screen quite quickly and simply. And I'm going to construct a Pixel Game Engine, quite a high definition one unusually. This case it's going to be 1600 pixels by 960 pixels, and there's going to be a one-to-one relationship between Pixel Game Engine pixels and screen pixels. I have my traditional onUserCreate and onUserUpdate functions, and right now all onUserUpdate does is grab the mouse coordinates on the screen and stores them as a floating point 2D vector.
You saw in the preview at the start of the video that we can pan and zoom around the screen, and I've already got a video that's just about this topic, so I'm not going to go into very much detail here. In fact, I'm just going to bring that code in and convert it to use our new vector type that we added in the last video. I've also added a couple of other features to the Pixel Game Engine, including the ability to draw dashed lines, which we'll see a little later on, and at long last, mouse wheel support.
The first thing I'm going to do is set this up to enable the panning and zooming and drawing of the axis and the world. And none of this is new stuff. In fact, I've done a video precisely about this topic, which you can click in the little link above. But to facilitate panning and zooming, we need to store some world transformation variables. And for this video, I will be going quite quickly through this. I've created numeric vectors that store the position of the offset and the start pan location. We also need a variable to handle the scale for the world transformation. Finally, I'm adding a variable called grid, and this is the spacing in world space between points that we're going to see on the screen. So all of my points are going to be 1 apart. Now, panning and zooming is all about transforming things from world space to screen space. So the first function I'll add, directly copied from the panning and zooming video and modified to suit the new floating point vector type, is world to screen, that takes in a vector in world space and gives me 2 screen coordinates as an output. We also want the inverse of that, screen to world. I'm going to set the default offset for our panning parameters to be the middle of the screen width and height. So that puts 0, 0 in world space in the middle of the screen. Everything else is now calculated per frame in onUserUpdate. Once I've got the mouse coordinate, I'm going to enable zooming by scrolling the wheel, but panning by holding down the mouse wheel and moving the mouse. So I want to be sensitive to the mouse wheel being pressed, and that's going to store the start pan location. As I have the button held down and move it around, I want to update my offset. So let's see quickly about drawing the world. Firstly, I'm going to clear the screen. And because I can see into the future, I know I'm going to need some temporary integer coordinates to represent locations in screen space. We only want to draw what we can see traditionally, so I want to work out what the visible extents of the world are. And to do this, very simple. I simply use our screen to world function with the top left coordinate of the screen and the bottom right coordinate of the screen. And this will give me the dimensions of the visible world in world space. I want there to be a little bit of overlap around the edge of the screen, just so when we're drawing lines, you don't see them clipping. So I'm flooring the left and top values, and I'm taking the ceiling value, i.e. rounding up, the bottom and right values. Because I know the extents of my visible world, I can simply have two nested for loops now that iterate along each axis, stepping in my grid size, because now we're iterating through world space. My grid was just set to 1. But I'll use the world to screen function to change this world space coordinate into the screen space coordinate and use that location to plot a pixel. Safe in the knowledge that it doesn't matter where I am in the world, I'm only drawing what the little window of the screen can see into that world. I also want to draw some axes into the world so I can see where my 0, 0 location is. And I'll do this by extracting a line from world space based upon the visible extents of the world, and I'll capture those in screen space in the SX, SY, EX and EY variables. And it's simply a case of drawing a line between those two coordinates, and I'm going to draw it in grey. But I'm going to just quickly and very sneakily show you a new feature that I've added to the Pixel game engine, which allows you to draw lines with patterns. And in this case you can specify a different 32-bit pattern, and it will just simply change pixels on or off depending on those bits. So I want these to be dashed lines, so I can do that by specifying this as the pattern, which says 4 pixels should be on, 4 pixels should be off, 4 on, 4 off, 4 on, 4 off, etc, etc. In this case, by clamping the X coordinate to 0, I've extracted the information for the Y axis. And I can do something similar to extract the information for the X-axis. Let's take a quick look. So there we can see we've got the axes going through the middle of the screen. That's good, that's my 0, 0 location, and I'm going to hold down the middle mouse button and move the mouse around, and the world is panning. You might not be able to see the faint blue dots on the YouTube video, but they are there. Switch it over to full screen. As shown in the panning and zooming video, zooming is a little bit more complicated. The principle is that we look at where the mouse is before the zoom, look at where it is after the zoom, and then translate the screen by that difference. And that allows you to zoom in under the mouse cursor, i.e. the pixel that is under the mouse cursor will remain under the mouse cursor. So that gives you a very intuitive to use zoom. So here I've took my mouse coordinates and worked out where my mouse is in the world. I'm now going to respond to user zoom commands, and I'll do this in two ways. Either they can hold the Q button down, or they can scroll the mouse wheel, and this is a new function too. In this case we're zooming in, we want to scale things up, so we change our scale value by making it larger. On the other hand, if the user presses the A key or scrolls the mouse wheel backwards, they'll zoom out. And the reason I've included the keys as well is if you're watching this on a laptop and you don't have a scroll button, you won't be able to zoom in and out very easily. Once the scale value has been changed, we need to now calculate where the mouse is again in world space, and then translate the world by the difference between the two mouse positions. Let's take a quick look. So I'm panning and I'm changing my mouse wheel, and you can't maybe see it very clearly if the blue dots aren't showing up, but we are certainly zooming in. And we zoom in relative to where the mouse cursor is on the screen. Very nice. I'm going to add an additional variable now, another vector floating point type called vCursor. And that's going to represent where the mouse is in the world. But why is it different to the regular mouse cursor? Well, in order to draw things accurately and cleanly, it helps if the cursor can snap to a particular location. So in this case, I want the mouse cursor to snap to the nearest unit value, or our grid spacing, in world space. And this is a very simple calculation to do. This means that the user can't select anything in between the grid values. Since we now have a snappable cursor, I'm actually going to draw that on the screen by drawing a small circle around the snapped location. And I'm also going to display its coordinate via text using the drawString function. So let's take a look. So we can see a little yellow circle representing the nearest grid point that the cursor has snapped to. In fact, if I zoom in quite a bit, you can see it doesn't move around continuously like the mouse cursor does, it snaps to the nearest location. And panning and zooming works just fine too.
So that's very nice. It might even be worth wrapping up panning and zooming into some sort of reusable container I can use in future videos and applications. But I'm not going to do that today. So let's get on with programming our class structure.
We know that for this simple demonstration, I'm going to need a structure that represents a node and a structure that represents a shape. Now our shapes are going to contain nodes, and our nodes contain pointers to shapes. So we've got a bit of a circular reference. I can solve that quite quickly by forward declaring my shape above the node. Our shape contains a vector of nodes. But because I've planned ahead, and you need to do that when working with polymorphism and object-oriented programs, I know that I want to specify what the maximum number of nodes is a particular derived shape can have. For most of the shapes it's 2. A line has a start and an end. A box has a top left and a bottom right. A circle has a midpoint and a point on the circumference. My shapes also are going to have a colour, and we'll start them off by them being green. My shapes are going to be responsible for drawing themselves, so I'm adding a virtual function in this case, and it's a pure virtual function. I've put the equals 0 at the end, and so this is indicating to the compiler that derived classes from S-shape must provide an implementation of the draw yourself function. And in this case, it takes a pointer to the Pixel game engine. Because I've defined S-shape outside of the Pixel game engine, I pass a pointer of it into the draw yourself function, so it can access all of the familiar drawing tools we have available. The user defines shapes by placing nodes, and these nodes belong to the shape that's currently being drawn. So I'm going to make it the case that the shape is responsible for creating the node and giving it to the rest of the application to handle appropriately. This is going to be the same for all shapes, so I don't need to make this method virtual. It's called getNextNode, and it takes in a position in world space, creates the node if it can, and returns a pointer to that node. The number of nodes a shape can have is governed by the nMaxNodes variable. So if we've already reached that value, then we'll just return null pointer. We can't create any more nodes, the shape is complete. For example, you can't have 3 nodes on a line, you can only have 2. Else if there is room for more nodes, then I'm going to create a new instance of a node and add it to my vector of nodes. And now you'll notice something truly horrific, something I've done a video about telling you not to do. I'm returning a pointer to the location of an element in a vector. Very, 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 very bad. However, what we'll see in a minute is we can do this quite legitimately, providing we're quite careful on how we set up the vector in the first place. Now, all of our shapes are responsible for drawing themselves, and they don't have access to the world-to-screen transform information. But since this information is going to be the same at all times for all shapes, I'm going to create 2 static variables to this structure, called worldScale and worldOffset. And I'm also going to provide a local implementation of the world-to-screen transform. So the shape can actually do this transform for itself. It doesn't need the screen to world one, that doesn't make any sense. The shape only exists within world space. We know that our shapes are going to have derived classes that override the draw yourself function to distinguish themselves from each other. Circles are not drawn the same as lines, for example. However, all of these shapes are responsible for drawing their own nodes, and this doesn't change per shape, so we may as well also include in our base structure the facility to draw the nodes of the shape. And this works in a very similar way. We'll pass a pointer to the Pixel game engine into a drawNodes function, iterate through the vector of nodes, take the node's location and transform it from world space to screen space, and then draw a little red circle at that location. We mustn't forget, whilst I'm at the bottom of the structure, that we've added two static members to this structure, so we must initialize them. And I just want to demonstrate that our S shape structure is abstract by trying to create an object of it directly. You'll see it doesn't like it, and it says object of abstract class type S shape is not allowed, and it goes ahead to tell us that the draw yourself function is a pure virtual function, i.e. it can't find any implementation for it, so we've protected ourselves from writing code that functionally wouldn't work. I appreciate that this video moves a lot quicker than most of my others. But now we've got this set up, we can start to see some of the benefits of thinking in terms of objects and polymorphism. So let's create the simple line structure. My line structure inherits from my base shape structure, and I'm going to give it a constructor. And in this constructor we set the maximum number of nodes this shape can have to 2. The line can have a start and an end. Now remember before where we did something which was an example of absolutely horrific practice. We returned a pointer to the element of a vector. Well, that's bad because vectors can move their contents around without you knowing, so the pointer can become invalid. However, we know how big that vector is going to be. For a line, there's only ever going to be 2 nodes. So I'm going to tell that vector, go and reserve 2 nodes worth of space please. This means the vector won't be reorganized beyond our control. It's the same as declaring an array in this instance. And because the draw yourself function was abstract, we must provide an implementation for it in this derived class. And we can signify to our compiler that actually, look, hello, we want to override this draw yourself function. This keyword is optional, but I think it gives you a nice little visible tick to say you are overriding a virtual function in a base class. Drawing a line is quite simple. We want to take the coordinates of the 2 nodes that we have in world space and convert them to screen space, and simply draw that line. I'll now add to our application class a pointer to a line. Once we've handled all the panning and zooming and snapping, we can start handling the remainder of the user interface. For a line, I only want to create one if the user presses the L key. This signifies that we're going to create a new line. I'm also going to add a pointer to our node, and I'll call that selected node. So at any given point, whatever node is pointed to by selected node is movable by the mouse cursor. I'll default that to null pointer. I'm going to assume that the user pressed the L key at the starting point of the line, so I'm going to set my selected node variable to whatever is returned from the getNextNode function of the line shape, which if you remember turns the current location passed to that function as a node. Since that's the first node placed, I don't really want to move that around with the mouse straight away, so I immediately want to get the second node, because that is the one I'm going to move with the mouse. As I move the mouse around, any node pointed to by the selected node pointer, I'm going to set its position to my snapped cursor location. As I click with the mouse, I want to continue placing nodes until the shape tells me there are no nodes left to place. If the shape returns null pointer when the getNextNode function is called, then the shape is complete, i.e. there are no more nodes available to define it. If the shape is complete, I'm going to set its colour to white. Once I've drawn my dots and my axes, I want to draw my line. So I'm going to call the draw yourself function and the draw nodes function, and pass in a this reference, which is the Pixel game engine, into those structures so they can draw themselves. But I don't want to do this if my line is equal to null pointer. Before we can draw any shapes, however, we need to set the static variables in our base shape class to set the scale and offsets for the world to screen translation. Let's take a look. I'll zoom in a little bit. I'm pressing the L key, which has placed the first node, and it's also placed the second node, but the second node is now attached to the mouse cursor, and the first and second nodes are used by the line shape to determine the start and end of the line. So we can see it's green, and it currently follows the mouse cursor around until I click. And we've defined the line shape.
We've now almost finished the skeleton application. We can pan and zoom, and we have the facility to add a simple shape, in this case a line. but I think for our application to be useful, we want to add multiple shapes, or at least multiple lines. So I'm going to create a list to store our line shapes in.
Changing our application to hold multiple lines is actually quite simple. I'm going to use a standard list to do this, and create a new list called list of shapes. I'm also going to create a temporary variable called tempShape, which is going to represent the line that we're currently trying to draw on the screen. So once the line has been confirmed, it gets added to the list of shapes. Whereas before we created a new line directly, now we're creating a temporary shape. We can determine what the mouse behavior implies by knowing if tempShape is set to null pointer or not. So if tempShape is not equal to null pointer, then we're currently trying to draw a shape. We're not just moving the mouse around on the screen. So if we're trying to draw a shape, then as before, we see if there are any nodes available left for the shape. If there are no nodes left, then the shape is complete. So it's no longer temporary. In fact, we want to push it to our list of shapes. We also want to change the drawing code for our temporary shape. Now the temporary shape is the instance currently being drawn, but we also have a list full of shapes that also need drawing. So we'll do that before we draw the temporary shape, by iterating with a little auto for loop through our list of shapes. Let's take a look. So I'll press the L button, we draw a line and click, I press the L button, we draw a line and click. Perfect. Lots and lots of lines. I feel it's also very useful to be able to move the nodes once they've been placed. So we need to put a routine into our S-shape structure to tell us if we've hit any of the nodes contained within that shape. And this is a very simple addition. This function hitNode takes in a location in world space. It then iterates through all of the nodes for this particular shape and works out the distance between the node's position and the position we've passed in. If that distance is less than 0.01, we don't want to do a direct comparison because we're working with floating point numbers. It would very rarely return true. So it's better if we look at what the magnitude of the distance is between those 2 points. If it's close enough, we'll return the address of the node that's been hit, and we'll set our selected node pointer to the address of the node this function returns. If no nodes are hit, then we'll return null pointer. I'm going to respond to the M key being pressed to signify I want to move the node that is under the cursor. Firstly, I'll set the selected node to null, and then for all of the shapes that I've currently placed, I'm going to iterate through them and call the hitNode function on my cursor location. If any of these return something that isn't null pointer, then I'm going to set that to my selected node pointer and break. I've found a node and I've now set it to something I can control with the mouse. Let's just quickly try this out. So I'll draw a line and I'll draw another line. I'll put my cursor over the beginning of that first line and press the M key. And you can see I've now got a pointer to that node and I can manipulate that node with the mouse. Let's try the other end of that line. Very nice. So if I make a mistake whilst I'm drawing my lines out, I can go back and fix it.
Our list of lines is all very good. I can draw and manipulate unique lines on our canvas. I want to add more shapes now, so I could create additional lists to contain all of those shapes and at runtime try and sort it all out by checking what type is each object. But I'm not going to do that. Instead, I'm going to now exploit polymorphism.
And so yes, it's been a little while coming with a bit of complicated code so far, but let's get to it. Let's turn this now into a polymorphic application. Here we're restricted to objects that are of type line. But as we've been learning, we can use polymorphism. So I can actually set this to shape. And I'll do the same for our temporary shape. Now what we'll look at is where we press the L key to create a new line. We know that tempShape is of type shape, but we're attributing to it a new object of type line, and the compiler is completely fine with this. If you don't believe me, a quick check. It's working just fine. So we have a list set up to store a type of one object, shape, but we're quite happily shoving into that list lines. And in fact, as long as we adhere to the interface defined by shape, i.e. we provide something which implements this draw yourself function, we can add all sorts of objects to our list of shapes. In fact, let's do just that. Let's add the box shape. So I'm going to start by just cutting and pasting the line shape. And I'll change it to sbox. I need to change the constructor. Just as before, a box is going to be defined by 2 nodes. I don't want all of these comments again. So we'll reserve that in our vector of nodes. In the draw yourself function, instead of drawing a line, I'm going to draw a rectangle, where I pass in the top left coordinate and the width and the height. And that's an important distinction to make here. It's not the bottom right coordinate, it's the width and the height. So you need to calculate that based on the transformed world coordinates. So I've created a very simple derived structure from shape called box. Here was the code where we responded to the L key being pressed to add a line. I'm going to copy and paste that, and instead of the L key, I'm going to make it the B key for box. But this time, instead of adding a new line, we want to add a new box, and everything else can stay the same. Our selected node stays the same. Our manipulating the nodes stay the same. Our ending of the shape stays exactly the same. And our drawing of the shape stays exactly the same. Let's take a look. So as before, we've got lines. Now if I press the B key, it draws a box. We've added some quite different functionality to the application without changing very much of it. And that change in functionality has been entirely encapsulated within the box structure.
Perfect. We now have lines and boxes, and these are unique shapes, unique objects that contain their own drawing code. They've become encapsulated and self-contained. The nice thing about this is our application hasn't had to do any filtering of how to handle these shapes. They simply draw themselves. Our application sees them as nothing more than just a shape. And this is really the power of polymorphism. So let's add some more shapes.
We've now got a very powerful pattern to which we can start adding all sorts of unique functionality. Let's add a circle. Again, a maximum number of nodes of 2. It's going to be the midpoint of the circle and a point on the circumference. And we'll fill in the draw yourself function. Firstly, I can get the radius of the circle by just being the distance between the 2 points. And I'm going to draw a dashed line between those 2 points to represent that radius. And then I want to draw the circle itself. But don't forget we need to scale the radius by our world scale coefficient. Here is our code for adding a line. Here is our code for adding a box. We'll just add in exactly the same code, but this time we'll create a type circle. Let's take a look. Line, box, circle. And don't forget we can pick up the points and move them around. And we can have lots of shapes. This one here is a very, very small circle. There we go. Hopefully you can see this is a very powerful pattern now. So I'm going to add something a bit more sophisticated. This time it's going to be a spline. I'll call it curve. And it's going to take in 3 nodes. Because this simple curve type has an end point, a start point, and a point in the middle where the curve moves towards. I've done an entire video series just about splines, so please check that out. We know that when the user first tries to create the spline, it'll have placed a node, and immediately also issued a second node, which they can drag around. So if we've got less than 3 nodes, we're drawing the first line from the starting point to the middle point. If we have got 3 nodes, we've got enough information to draw both the structural lines of the spline, but also the curve itself. So I'm drawing those structural lines as dashes, but I'm also going to then iterate with a small step along the curve and draw it out to the screen. In fact, in this code, I'm breaking the curve into lots of little line segments and drawing those. So the curve shape is a little bit unique. It requires more information in order to place, and it also draws itself differently depending on how much information that it's got. But this difference in functionality is entirely encapsulated within the curve shape. we don't need to change any of our application in order to facilitate adding curves. So I'll respond to the S key in this instance to add a curve. Spline. Let's take a look. Press the S key. So we've only got 2 nodes on the screen so far, so it's a structural line. If I click, it then allocates the second node and starts to draw the curve. And click again to complete it.
And so there you have it, a simple demonstration of using polymorphism to add features to an application without changing the underlying nature of that application. A very powerful tool. But as with all things object-oriented programming, we really need to think about it in advance. It's no good just jumping in at the deep end and writing lots of code and hoping it's all going to come together. That's called spaghetti code, and it will be barely maintainable and probably won't work, and you'll end up doing several rewrites. So I really recommend sitting down and thinking about your application before developing it. Anyway, all of the code for this video is available on GitHub. Please download it and make some modifications, add some new shapes even. If you've enjoyed this video, a big thumbs up please. Have a think about subscribing, come and have a chat on the Discord, and hopefully I'll be back in my normal programming place next time. Take care.